Hello everybody, welcome to this NPTEL course on Material and Energy Balances. I am Dr. Vignesh Muthuvijayan. I am a faculty in the Department of Biotechnology, IIT Madras. During this course, we will look at some of the most fundamental aspects of material and energy balances and look at how these can be applied eventually into higher level courses. Before we delve into basics of material and energy balances, we first need to understand the fundamentals associated with any engineering calculations. This will be the first lecture of this course. The most important aspect of any fundamental calculation which is being performed would be the units and dimensions. What are units? Units are basically definite magnitudes of any quantity. Any measurable quantity would have two things. One is a numerical value and the other is the units. 60 seconds would represent time, 5 meters would represent distance or length, and 70 kilograms would represent mass. Without units, these numbers do not have any physical significance. They will just stand as pure numbers. Using units carefully has a lot of practical advantages. It ensures that you understand the physical meaning of the number which is being given. I do not have to clearly state that the time taken was 60 seconds. If I just say it took 60 seconds, you would automatically know its time that I am talking about. So, the physical meaning of the number is clearly understood when the units are actually associated with the number. It minimizes errors in calculations. When you ensure that all the numerical values which you are using in your calculations are accompanied by the units, you will also make sure that the units tally with each other and you use appropriate conversions. Thereby, you can minimize the calculation errors which usually come due to failure to convert one unit to another. It also gives a way to establish a logical approach towards calculations rather than memorizing formulae. What are dimensions? Dimensions are the basic concepts of measurement. Examples would be length, mass, time, etc. Dimensions can be calculated by multiplying other dimensions or dividing two dimensions. Examples would be speed, force, energy, acceleration, and so many other things. One dimension can actually have multiple units. For example, length can be measured in terms of inches, meters, miles, light years, and so many other terms. So, similarly, time can be measured as seconds, minutes, hours, days, weeks, and so on. When you are talking about units and dimensions, there are certain points which you need to remember. Numerical values can be added only when they have the same units. Different units can be combined by multiplication or division. Units can be converted from one unit to another using conversion factors. 1 kilogram can be converted to grams by multiplying it with a conversion factor of 1000. Here is an example where we try to perform this kind of a unit conversion. Let us look at doing a systematic approach to ensure that we minimize errors in calculation. The problem statement is, studies have shown that Vibrio cholerae, the cholera causing bacteria, moves at a speed of 100 micrometers per second. What is its speed in kilometers per day? So, the information which has been given to you is in terms of micrometers per second, and they want this to be converted to kilometers per day. So, the micrometer needs to be converted to kilometer and the second needs to be converted to day. So, let us go about solving this. 100 micrometers per second is the data given. We know that 1 micrometer is 10 power minus 6 meters. So, 1 meter divided by 10 power 6 micrometers is multiplied to the given value. Now, this meter can be converted to kilometer as 1 kilometer contains 1000 meters. So, now we have technically converted micrometers to kilometers. We now need to convert the seconds to days. We know that 1 hour contains 3600 seconds and 1 day contains 24 hours. Using these values, we would finally get kilometers per day. We can even verify this. So, the micrometer given in the speed cancels off with the conversion factor given, and the meter taken in the conversion factor again cancels off with the second conversion factor. The second cancels off with the first conversion factor and the hour cancels off in the second conversion factor for time. Thereby, your final units are kilometers per day, and you end up with a value of 8.64 times 10 power minus 3 kilometers per day. If you looked at how I did this problem, I have written down each number with the associated units and the conversion factors were also written along with the units. This ensures that I can appropriately use the conversion factors either for multiplication or division. This will eliminate any confusion and ensure that I do not randomly multiply or divide and make unnecessary conversion errors. The units which we use have different systems. There are 3 different systems which are commonly used. The first system is the SI units, which is the most accepted system of units amongst engineering and scientific community. You also have CGS system, which is very similar to the SI units, except for the fact that length is measured in centimeters and mass is measured in grams instead of meters and kilograms, which would be used in SI units. Other fundamental units are similar to the SI units. American engineering units is another popular system which is commonly used in the US. Outside of US, it is not very common to use American engineering system because there are some inherent problems with this. The conversion factors which are used in American engineering system are not multiples of 10. This makes it very tedious to remember the conversion factors and perform the conversions. For example, 1 yard actually is 3 feet and 1 mile is 1760 yards. It would be very difficult for most people to remember these numbers and apply them correctly. Another problem associated with the American engineering system is the unit for force. The unit for force in American engineering system is pound force. This has inherent problems in conversion. We will look at what that is in the later slides of this lecture. For now, let us take it by face value that pound force causes problems with conversion. So, the units can be classified into different types. How are they classified? The first type is the fundamental or base units. These are the units that can be measured independently. So, example would be a length which you can measure using a scale and so on. You also have derived units, which are terms derived from the fundamental units either through multiplication or division. So, we told that there are base or fundamental units. So, how many base or fundamental dimensions and units are there? You would have studied this in your high school and you should be familiar with this already. There are 7 fundamental dimensions or units. Okay, what are they? What are these fundamental dimensions and what are their units? The first fundamental dimension is length. The SI unit for length would be meters, CGS unit would be centimeters, and American engineering unit would be foot. Mass is measured as kilograms, grams and pound mass in the 3 systems. Moles, which is the amount of substance, is measured as gram moles in SI units and CGS units, and it is measured as pound moles in American engineering units. Time is measured as second in all the 3 unit systems. Temperature is measured as Kelvin in SI and CGS units and as degree Rankine in American engineering units. These are the 5 fundamental dimensions and systems which we keep using throughout this material and energy balance course. In addition to these 5 fundamental dimensions, you also have electric current and luminous intensity, which are measured as ampere and candela in the SI units. We will not be using these 2 dimensions for this course. Moving on to the derived dimensions and units, these are obtained by multiplying or dividing base units or dimensions. One example could be the unit for speed is given as meters per second. So, you could also have units which are defined as equivalents of these compound units. So, the examples are given here. Volume is measured in liters, which is basically 0.001 meter cube. So, similarly, there are different derived units for force, pressure, energy and power. Force in SI units is given as Newton, pressure is given as Pascal, energy is given as Joule and power is given as watts. So, this table gives you the dimensions of these terms and the units which are given and the symbols which are used for the SI units and also their equivalents in the for the compound units. Now, let us take one of the derived units, which is force. So, this derived dimension force is defined by second law of motion by Newton, which is force equals mass times acceleration. Units for this are kilogram meter per second squared, gram centimeter per second square and pound mass feet per second squared in the 3 systems. So, it is simple, mass is kilograms and acceleration is meters per second squared. So, this gives you kilogram meter per second squared. So, these derived compound units can also be written as derived units as Newton in SI units, dyne in CGS and pound force in American engineering units. 1 Newton is defined as 1 kilogram meter per second squared. 1 dyne is defined as 1 gram centimeter per second squared. However, in American engineering system, 1 pound force is defined as 32.174 pound mass feet per second squared. This is because a pound force is defined as the product of a unit mass and acceleration due to gravity at sea level at 45-degree latitude. Because of this definition for pound force, there is an inherent problem with conversion whenever we use pound force term. To avoid this and overcome this, we use something called GC, which is the conversion factor. So, let us look at an example problem which will hopefully help us understand how to use this conversion factor GC. The problem asks you to calculate the kinetic energy in terms of pound force times feet for a 10 pound mass weight moving at a speed of 10 feet per second. We all know that kinetic energy is given as 1 by 2 mv squared, where m is the mass and v is the velocity. So, if we were to apply the values which have been given to us, so we would directly get 1 by 2 times 10 pound mass times 10 feet per second whole squared. This gives you a value of 500 pound mass feet squared per second squared. So, this is the value you got for kinetic energy, but the problem asks you to calculate kinetic energy in terms of pound force feet, which means the pound mass feet squared per second squared term in this value you have calculated needs to be converted to pound force. For this, we would use the conversion factor GC. So, GC is 32.174 feet times pound mass divided by pound force second squared. So, we apply this GC to the equation which was given earlier, thereby we get 500 pound mass feet squared per second squared times pound force second squared divided by 32.174 feet pound mass. So, basically what we have done here is divided the kinetic energy which was calculated in terms of pound mass feet squared per second squared by GC, giving you a final value for kinetic energy as 15.54 pound force times feet. Hopefully with this you understand how to apply this conversion factor. If you can remember that GC is the factor which is basically numerically equal to the acceleration due to gravity at sea level at 45-degree latitude with the units of feet pound mass per pound force second squared, you would be able to apply this appropriately to make all the conversions. Other than these dimensions and units, there are also terms which are dimensionless. There are pure numbers like I, pi, Avogadro's number, which do not have any dimensions. You also can have combinations of variables with no net dimension. Basically, there could be ratios of different terms where the dimensions get cancelled off. Examples would be mass ratio, specific gravity and Reynolds number. When we talk about dimensionless numbers, we need to understand that there can be dimensionless numbers and unitless numbers. When I say dimensionless, it does not mean that the quantity is unitless. Some of the dimensionless quantities can have units, whereas all the unitless quantities are dimensionless. The example would be mass ratio technically has units of grams per gram, where it would be grams of one component divided by the grams of mixture or the grams of other component. Dimensional homogeneity is something which needs to be verified and valid for every equation. All valid equations would have uniform dimensions. By that what I mean is the left hand side of an equation and the right hand side of the equation should have the same dimensions. Another important parameter is all additive terms in an equation need to have the same dimensions. Here is an example problem. You can check the first statement which I have made. I have said that valid equations would have uniform dimensions. Now we know that potential energy is given as mass times acceleration due to gravity times height, which is mgh. Can you verify if this equation is dimensionally correct? Let us go to the first principles and try to identify what would be the dimensions of the left hand side. The left hand side term is energy. Energy is defined as force times distance. Force is defined as mass times acceleration. So energy is basically mass times acceleration times distance. So we know that the dimensions of mass is m, dimensions of acceleration is L t power minus 2 and distance is L. Therefore, it gives the total dimensions of the left hand side as m L square t minus 2. Now, let us calculate the dimensions for the right hand side. It is mass times acceleration due to gravity times height. Dimensions of mass is m, dimensions of acceleration due to gravity is L t power minus 2 and height is L, thereby again giving m L square t minus 2. So, based on the dimensional homogeneity, we can say that the dimensions of the left hand side are equal to dimensions of right hand side. This proves that this equation is dimensionally homogeneous and correct. So, let us try another example problem where we try to identify the dimensions of constants which we do not know. Van der Waals equation is based on plausible reasons that real gases do not follow the ideal gas law. So, we all know that ideal gas law is PV equals nRT. In real cases, gases do not follow this, and Van der Waals equation is one of the model equations which describes such a real gas. So, the equation is given as P plus n squared A divided by V square times V minus NB equals nRT. Here P is pressure, V is volume, N is the amount of substance, T is temperature, and based on dimensional homogeneity, you have been asked to calculate the dimensions of the constants A, B and R. So, to do this, we first can take the first term alone. So, the first term which we have here has two aspects. One is the pressure and the other is the term which contains A. These two are added. Based on our rules for dimensional homogeneity, any additive term has to have the same dimensions, which means dimensions of P should be the same as the dimensions of the second term, which is n squared A divided by V squared. So, let us try and identify what are the dimensions of P, which is pressure. Pressure is defined as force divided by area, and force is defined as mass times acceleration divided by area. So, now using this, the dimensions for mass is m, dimensions for acceleration is L t power minus 2 and dimensions of area is L squared, thereby the dimensions of the term pressure is m L minus 1 t minus 2. So, this means the dimensions of the term n squared A divided by V squared would also be equal to m L minus 1 t minus 2. V being volume, we know that the dimensions of the denominator here would be L power 6, which is L cube squared. N squared is basically the square of amount of substance. So, if we were to have that as n as the dimension for amount of substance, it will be n squared times A equals m L minus 1 t minus 2. So, this implies dimensions of A would be m L power 5 n minus 2 t minus 2. Moving on to the next section, we will have to calculate the dimensions of the second term B. So, let us look at this equation. Based on this, the dimensions of V, which is volume, should be the same as the dimensions of the term NB. So, dimensions for volume is L cube and the dimensions for N, which is amount of substance, is N. So, which means the dimensions of B would be L cube n minus 1. So, we can actually perform these calculations more systematically if we want to. So, what we can do here is we can actually assume the dimensions of each of these terms as m power x, L power y, t power z and n power a and so on, and solve this equation to get all the powers which are there. So, I am just doing it in a simplified fashion, assuming that most of you would be familiar with how to perform these calculations. If you have any queries, feel free to contact me. So, now we can calculate the dimensions of R basically using the rule that dimensions of the left hand side should be equal to the dimensions of the right hand side. So, the dimensions of the left hand side is basically the dimensions for pressure, which is the first term, and the dimensions for volume, which is the second term. So, now the left hand side is basically P times V, which is pressure is m L minus 1 T minus 2 times volume being L cube, giving you a dimensions of m L square T minus 2. So, the right hand side would also have the should also have the same dimensions. So, we know that the right hand side basically has n, which is the amount of substance, and whatever is the dimensions for R, times theta, which is the dimensions for temperature. So, we know that m L square T minus 2 should be equal to n dimensions for R times theta. So, this implies that dimensions for R is m L square T minus 2 n minus 1 theta minus 1. Based on this, we have performed dimensional homogeneity calculations to identify the dimensions of constants A, B and R. Moving on, we will move to the next important concept when it comes to engineering calculations. It is called significant figures. Before we learn how to identify the number of significant figures and why we use them, how we use them, let us look at this example problem. When you are measuring the mass of some substance 3 times using a balance with a readability of 0.001 grams, you will probably get values like this. So, the trial 1 has given you a value of 47.476, trial 2 has given you a value of 47.453 and trial 3 has given you a value of 47.498. Now, if you were to calculate the average of these 3, which you can assume to be the closest to the accurate mass of the substance you measured, you will end up with a value something like 47.475666667 grams, which is what your calculator or Excel would give. However, the value which you have written down here is more accurate than all the values that you have measured, because the readability of your weighing balance was only 0.001 grams, and here you have written a final value which is much more accurate than that. This cannot be true. The final answer which you write down cannot be more accurate than your readings. If you have a value of that sort, then you do not have physical meaning for the numbers that you have written. So, to know and understand these significant figures and use them, we first need to know how to count the number of significant figures for any given number. If the number does not have any decimal points, then what you do is you start with the first non-zero digit on the left and start counting the number of digits till the last non-zero digit. So, if I were to have the example of 9547, this number would have 4 significant figures, where the first non-zero digit on the left is 9 and the last non-zero digit is 7. However, if I were to use a number like 9500, then I have only 2 significant figures, because the first non-zero digit on the left is 9 and the last non-zero digit is 5, giving me only 9 and 5 as the significant digits. If there is a decimal point, then what you do is you count the number of digits from the first non-zero digit on the left to the last digit. It does not matter if your last digit is 0 or non-zero. Example given here is 9.5470. This would have 5 significant figures. Because there is a decimal point, I will start from the first non-zero digit on the left, which is 9, and go all the way to the last digit, which is 0. So, that gives me 5 significant figures. If I were to use the second example, which is 0.009547, I still start with the first non-zero digit on the left, which is still a 9, and I go all the way till the last digit, which is a 7, thereby giving me only 4 significant figures. If you write these numbers in scientific notation, then there is a clear representation of this significant figures. Why should we bother about these significant figures. Any measurement which we report is limited by the accuracy of the measuring device itself. Whatever number we use cannot be more accurate than whatever we measured. That was the example which we looked at. Consider the same example. The weighing balance had a readability of 0.001 grams. What does this mean? If my substance has a true mass of 8.3426 grams, the balance would round it off and give it as 8.343 grams, because the readability of this balance is only till 0.001 grams. Similarly, if the mass of the weighed substance is actually 8.3434 grams, the balance would still read it as 8.343 grams. It cannot account for the last 0.0004 grams. What this means is, any value between 8.3425 and 8.3435 will be represented as 8.343 by the balance which has a readability of 0.001 grams. So, the last significant digit which you have can actually be off by as much as half a unit. This has a lot of physical significance, and that is why you need to ensure you follow the number of significant figures which are present. When we perform arithmetic operations, we need to use significant figures carefully. We need to know how to write the final answer with only the significant figures. If we were to perform multiplication and division, you would have to count the number of significant figures of the multiplicands and divisors and decide that the number which has the lowest number of significant figures is the maximum with which you can go. So, the example given here will illustrate this. You have 4.027 times 309 giving you a value of 1244.343. So, this is what your calculator would give you. However, the first term, which is 4.027, has 4 significant figures, and the second term 309 has 3 significant figures. So, the most number of significant figures, your final answer, which is the product, can have is 3 significant figures. So, you would write down your answer as 1240 to match the significant figures. This will accurately represent the physical validity of the numbers which you have used. Here is another example problem. 17.1 times 10 power minus 3 into 0.1327 times 10 power 5 divided by 2.3472. If you were to plug these values into a calculator, you would end up with 96.6756135. This is mathematically accurate, but physically it is not. So, what you do instead is, you need to identify what would be the appropriate number of significant figures which you can use. Now, can you identify how many significant figures your final answer should have? Let us see this. The first term 17.1 has 3 significant figures, and the second term 0.1327 has 4 significant figures starting from 1 to 7. The denominator has 5 significant figures, 2 to 2. So, the lowest number of significant figures in your multiplicands and divisors is for the first term, which is 17.1 times 10 power minus 3. So, your final answer can also have only 3 significant figures, and this means you would write your final answer as 96.7. So, this gives you the answer with the proper significant figures. If you were to perform addition and subtraction, then you need to use a different strategy to identify the correct number of significant figures for the final answer. The position of the last significant digit of each number relative to the decimal point has to be compared. The one which is farthest to the left is the position of the last permissible significant figure for the sum or difference. An example problem will illustrate this condition clearly. The example problem given here is 2.450 minus 0.0217 plus 12.32. Giving this in a calculator, you would end up with 14.76783. Although this is numerically correct, it is again physically not accurate. So, what you do is identify the position of the last significant digit in each of these numbers relative to the decimal point. For the first number 2.450, the last significant digit is the 1000th digit, which is 0. For the second number, the last significant digit is the 1/10,000th digit, which is 7, and the third number has the last significant digit as the 100th digit, which is 2. So, your final answer can actually be written only till the 100th digit. Thereby, you will write down the final answer as 14.77. Please understand that using these significant figures ensures that physical meaning of the measurements you have done is conveyed through the final answer. At the same time, I would strongly recommend that you do not round off every step to get to significant figures, because it will add up to the errors which you finally calculate. So, rounding off can be done at the end. After performing all the calculations and after using significant figures to represent the physical meaning, ensuring that the units and dimensions are accurate and everything, you can still make mistakes. To ensure that you have not made mistakes, there are different ways to validate the calculations which you have performed. The technique used for validation will depend on the time and money available to you. So, if you need high powered computers to perform the validation, the cost is going to be a problem. If you are in an exam hall and you have 10 minutes left before you submit the answer sheet, then time becomes a problem. Considering what is available to you, you can use one of the following methods. You can repeat the calculation, possibly in a different order. This will ensure that you perform all the calculations again, and because it is coming in a different order, it will ensure that you do not make the same mistake again. You can also do back substitution, where you take the solutions you obtained and substitute it back to the equations which you wrote down and ensure that these equations are still valid. You can do something which is a little simpler called order of magnitude estimation. So, basically whatever calculations you are performing, you would have used different numbers. These numbers would have their own orders of magnitude. Based on this, you can roughly estimate what would be the order of magnitude of the final answer you are expecting. If the final answer you have gotten is in the same order of magnitude, chances are you have not made a gross mistake. If it is in a different order of magnitude, then there is probably some crucial mistake which you have committed, quite possibly due to unit conversions or multiplying something instead of dividing it and so on. So, the last and the crudest form of confirming the answers would be test of reasonableness. Does the solution you obtain make sense? This seems so simple and trivial, but many a times people do not think about it very carefully, especially in an exam setting. People do not look at whether the numbers which they have written down are actually physically meaningful. For example, many a times students write down the final answer for a flow rate, which could be the mass flow rate or volumetric flow rate, as a negative term. Flow rate for mass cannot be negative, it has to be a positive number. This makes no sense. However, people do not think about it in the speed of the exam and try to hurry and submit something, thereby making an unnecessary silly mistake. So, these techniques are actually useful for you to ensure such errors do not crop up in your calculations. Please use these techniques, ensure that all the calculations you perform are accurate. I hope that whatever we have covered today with respect to the units, dimensions, dimensional homogeneity, significant figures and the techniques for validation would give you all the ammunition you need to perform calculations accurately and ensure that you excel in this course throughout this program, and thank you.